Welcome to The Explainer. Today, we are unpacking the invisible architecture that literally keeps our modern hyper-connected world from completely falling apart. We're talking about fog and edge middleware. I mean, think about the sheer scale of the Internet of Things right now. Millions of devices, sensors, and servers. Without a highly structured system to manage the whole shebang, these massive heterogeneous IoT systems would instantly collapse into total digital chaos. But how exactly do we prevent that?
Okay, let's dive into this. Picture a state-of-the-art smart hospital. On just one floor, you've got Bluetooth heart rate monitors strapped to patients, Wi-Fi security cameras scanning the hallways, and low-power Zigbee motion sensors controlling the lights. These devices are speaking completely different languages, operating on entirely different network protocols, and generating data at wildly different speeds. It is an absolute cacophony of digital noise.
So here's our game plan for making sense of all that noise. We're going to cover bridging the IoT divide, the software glue that holds it together, the four-layer architecture, the math behind data aggregation, and finally, some real-world middleware examples. We'll logically build our way up from the messy hardware problem to the brilliant software architecture. Let's kick things off with part 1, bridging the IoT divide. You see, there's this massive chasm in modern network architecture. On one side, you have raw, chaotic IoT hardware. It's disorganized, it's erratic, and very localized. And on the other side, pristine, highly organized, immensely powerful cloud servers. Connecting these conflicting edge devices directly to a centralized cloud, that guarantees total system failure. The cloud simply isn't built to untangle millions of varying, localized protocol streams in real time. So, the crucial point here is this. Hardware without software is really just an expensive space heater. Seriously. All those incredibly advanced physical edge devices are completely useless without a specialized translator sitting right in the middle, bridging the gap between that chaotic physical world and the organized digital cloud. Which brings us to part 2, middleware, the software glue. The definitive answer to that massive translation problem we just talked about is middleware. By standard definition, it's a software layer sitting right between the operating system and the applications. But really, in the fog and edge computing ecosystem, it acts as the ultimate software glue. It completely masks the insane complexity of all that underlying IoT hardware. Because of middleware, developers don't have to worry about the physics of a Zigbee antenna or the specifics of a Bluetooth packet. They can focus purely on writing brilliant applications.
Now, for middleware to actually be effective, it's built on 4 critical design goals. We have interoperability, resource discovery and management, location awareness and mobility support, and finally, security and privacy abstraction. But I really want to emphasize the very first one on that list, interoperability. It is absolutely the most crucial pillar of the whole system. Interoperability basically means the middleware can take varying lightweight messaging protocols, things like MQTT or CoAP, alongside your standard HTTP, and translate them all into one unified standard format. It ensures that a temperature sensor made by brand A can seamlessly talk to a processing algorithm designed by brand B. Meanwhile, those other 3 goals, they're handling the rest of the chaos. The middleware autonomously tracks moving nodes like connected cars driving through a city. It dynamically allocates CPU memory without any human intervention, and it handles local encryption so sensitive data never leaves a local network in plain text. Let's move to part 3 and see how this builds into the 4-layer architecture. To understand how this structures into a service-oriented system, we use a classic 4-layer stack, building from the bottom up. Down at layer 1 is the physical infrastructure. This is exactly what it sounds like, folks. The messy, real-world sensors, actuators, edge servers, and fog routers. It's the raw physical foundation of the entire setup. Right above that is layer 2, the abstraction or virtualization layer. This is where the magic really starts happening. This layer takes all those raw physical signals and translates them into standardized digital formats. It uses API gateways to turn those lightweight IoT protocols into standard web traffic, and it leverages container engines like Docker, making the hardware actually ready to host complex microservices. Moving up, we hit layer 3, the service management layer. Think of this as the brain of the middleware. It aggregates data, enforces security rules, and schedules tasks. And because layer 3 handles all that heavy lifting, it enables layer 4, the application layer, to function perfectly. Layer 4 is where the end user lives. Application developers just tap into REST APIs to get clean, beautifully organized data to power smart city UIs or healthcare machine learning models. They are completely blind to the hardware chaos happening way down in layer 1, and that's exactly how we want it.
All right, let's pick up the pace a bit for part 4, the math of data aggregation. How does layer 3 actually manage all this data without just crushing the network? Well, imagine a smart thermostat in an office building. It's blasting out 22 degrees Celsius every single second of every single day. Sending that unmodified repetitive noise all the way to the cloud, that wastes a massive amount of network bandwidth. So the middleware at the edge intercepts it. It takes dozens of these raw, redundant incoming streams, filters them, averages them, and outputs one single clean, thick, aggregated stream straight to the cloud.
And this brilliantly illustrates the concept of bandwidth saved, or delta B. It's simply the mathematical difference between the massive volume of raw incoming data streams and the much smaller, refined output going to the cloud.
Breaking these variables down quickly, you take the total number of sensors, multiply that by their individual incoming transmission rates and payload sizes, and then subtract the fog's outgoing transmission rate and compressed payload size. Because the middleware filters out all that repetitive noise, the outgoing payload is drastically smaller. This formula right here, this is exactly why middleware is entirely non-negotiable. If you want to scale an IoT architecture, you have to mathematically eliminate the bottlenecks at the edge. There's just no other way.
Finally, we arrive at part 5, real-world middleware examples. Let's see this in action.
So we've got the theory, the architecture, and the math. But what are engineers actually using in the industry today? Now, what's really interesting about these real-world tools is how specialized these solutions have become. You have EdgeX Foundry, an incredible open-source, vendor-neutral platform hosted by the Linux Foundation that heavily powers industrial IoT and factory floors. Then there's Apache Edgent, which is focused specifically on embedding data analytics right at the edge. And Phyware, a massive player in managing context data for sprawling smart city deployments. These aren't just theoretical concepts. They are the actual modular foundations of our connected infrastructure. We've seen how middleware acts as the ultimate software glue, taking unconnectable, chaotic hardware and translating it into clean, scalable, mathematically efficient data. It drastically reduces bandwidth and makes modern applications even possible. So as you look at the incredibly complex smart systems being built around us today, I want to leave you with this question to ponder. If hardware is just an expensive space heater without software, how will your next IoT design scale without breaking? Thanks for joining me on this explainer, and keep questioning the systems that connect our world.